Hola, Mr. Sutton here with the AB Calculus 4-5 Extra Practice Number 3 solutions on points of inflection. On this problem, we're trying to find inflection points for this function. So I'm going to need to know the second derivative on this. My first derivative, I'm going to have 2/3 times all of this to the negative 1/3 times the tail of 2 using our chain rule. So that's going to end up being 4/3 times all of that to the negative 1/3. And then for the second derivative, I'm going to have negative 1/3 times 4/3, so negative 4/9 times the tail of 2, so negative 8/9 times all of this stuff to the negative 4/3 power. And at this point, I'm going to rewrite this so that it's a little easier to analyze it for critical values. So I'm going to have an 8 in the numerator and 9 in the denominator. Also in the denominator, I'm going to have all of this stuff to the, I'm going to have the cube root of all this stuff to the 4th power. And that whole fraction is going to be negative. So a whole lot of form changing going on there. So in terms of critical values, since I have a constant numerator, there's no way to make this thing equal 0. However, I can make this undefined. F double prime does not exist if x equals negative 6, because that would zero out the denominator. We don't have to worry about taking roots of negatives because we have an odd root, but 0 in the denominator, that's still a thing. So now let's take a look at what's going on with the sign here. I mean, we could do some sign analysis around negative 6, but if you take a look at this, we're raising all this stuff to the 4th power, so that guarantees you're getting a positive result inside the cube root. The cube root of a positive is positive. A positive times 9 is positive. A positive divided by a positive is positive, and the whole fraction is negative. So f double prime is going to be negative for all x values except for that value of negative 6, which makes it undefined. Since there is no sign change in f double prime, that means there is no point of inflection. For this one, I'm trying to find points of inflection for 2 over x plus 3. So I need the second derivative, and to do a little analysis of that, let me start by rewriting this original function as 2 times x plus 3 to the negative 1. That'll make it a little bit easier to use my power rule. So now using that, my first derivative, I'm going to have negative 2 x plus 3 to the negative 2 power. And I'd multiply by the tail, but the inner derivative is just going to be 1, so we're not worried about that on this one. Now for the second derivative, negative 2 times negative 2, that's going to be a 4, x plus 3 to the negative 3rd. And I'm just going to rewrite this as 4 over x plus 3 cubed, just to make it a little easier to analyze things. Now looking for critical values, it looks like our numerator is a constant, so this can't equal 0. But we still have a critical value at x equals negative 3 because that makes our denominator 0. So f double prime then would not exist at x equals negative 3. There's just one problem though. At x equals negative 3, the function itself is going to be undefined. So that means that this cannot be the location of a point of inflection. And since there's no other candidates, there's no other critical values, that means there is no point of inflection for this function. On this problem, I'm given f double prime for a function, and I want to know where this has inflection points. So for that, I need to have some critical values, which I can find by setting f double prime equal to 0. And this is going to get zeroed out if x is going to be 0, or negative 1, or positive 2. So at this point, we're going to do some sign analysis. Let me set up my f double prime number line with negative 1, 0, and 2 on there. So doing some sign analysis, I'm going to try a number from each of these intervals. Before negative 1, I can try out negative 2. So let's see here. This x minus 2 squared, by the way, this is always going to come out positive, so we don't have to consider it while doing sign analysis. It's just these first two parentheses that could be negative or positive. So for this first one, this is going to be negative times another negative is going to give us a positive. And then between negative 1 and 0, we can try out negative 0.5 or negative 1/2. So that's going to give us a negative and a positive, which is going to be negative. And then finally, between 0 and 2, actually finally, there's 2 more to test. Between 0 and 2, we've got 1 we can try. That gives us a positive times a positive, which comes out positive. After 2, we can try 3. Which gives us a positive, positive, or positive overall result. So now with points of inflection, I'm looking to see where f double prime is changing sign. And I notice that I have a sign change at -1 and 0 for f double prime. Therefore, f has points of inflection at x equals -1 and 0, which is going to be answer choice C. On this problem, I'm given a function whose first derivative is defined as x cubed minus 4x, and we want to know at what x values this graph has a point of inflection. Now you got to be careful on this one because they've already given you f prime. So with points of inflection, you're always looking at where f double prime is changing sign, but again, note you already have f prime, so you just need to take one more derivative to get the function that you're going to analyze. So the second derivative then, that's going to be 3x squared minus 4, and we're stopping there with derivatives because we've got f double prime now. So setting that equal to 0 and solving, if I add 4, divide by 3, and then square root all of that, that's going to be plus or minus 2 over radical 3. And just looking at the answer choices, well, there's only one answer choice that it could possibly be. Our critical values are positive and negative 2 radical 3, and there's positive 2 radical 3. There's no choice for negative 2 radical 3, and there's no choice for none of these. So you could stop here and pick answer choice C, but just do a little sign analysis to really confirm the kill on this one. Here's my f double prime number line. I've got -2 over root 3, positive 2 over radical 3, and I'll test something on each of these intervals. So to the left of 2 over negative radical 3, I think -2 is going to be less than that. So plugging that into f double prime, that's going to be 12 minus 4, which is a positive. Between these critical values, we can test out 0. That's going to be 0 minus 4, which is a negative. And 2 is bigger than 2 over root 3. So that's going to be, let's see, 12 minus 4 again, which is positive. So we see that we do have f double prime changing sign at plus or minus 2 over radical 3. Therefore, we have points of inflection at positive and negative 2 over radical 3. So it was definitely choice C. For this problem, we have a function defined on 0.4 to 2.4 with a first derivative given by f prime of x equals sine of x squared. We want to know which of these statements is true. So we're talking about relative maxes, relative mins, points of inflection. It'd be very helpful if we actually knew what this function looked like, or what the f prime looked like. So this is a calculator question. Let's go ahead and graph that. So here I am on the calculator in y equals. I've entered my f prime function right here. And let me go to window. And since they're talking about the interval 0.4 to 2.4, I want that exact window so that I can analyze this properly. So 0.4, 2.4, and then let's do zoom 0, zoom fit, and see what this thing looks like. So there's my f prime. And I notice, so here's a picture of this, I notice on the interval from 0.4 to 2.4, f prime is changing from positive to negative, which means that we're going to have a relative max somewhere on that interval. We don't actually need to figure out where it is. They didn't ask where it is. We just know that it's between 0.4 and 2.4 because that's what I set my window for on the calculator. Now, we don't change anywhere from negative to positive. So that means that we do not have a relative min. So option 2 is no good, but option 1 is good. So really, it's all down to whether option 3 is true or not. So this one, the graph has 2 inflection points. So points of inflection, that's where f double prime is changing sign. You could take the second derivative and graph that and see where it's changing sign. But a quicker way to do this, if f double prime is changing sign, that means that f prime is changing from positive to or changing from increasing to decreasing, or decreasing to increasing. In other words, f prime is going to reverse directions wherever f double prime is changing sign. So we notice that there are 2 places where f prime reverses directions on here. We're changing increasing to decreasing right here, and decreasing to increasing over here. Therefore, f must have 2 points of inflection on this interval. So it's going to be options 1 and 3 then, which is going to be choice D. For this problem, we want to know where the graph of y equals 5x to the fourth minus x to the fifth has a point of inflection. So for that, we need to know where y double prime is changing sign. And this is a no calculator question, so that's probably the easiest way to do this. So first, let's find what y prime looks like. That's going to be 20x cubed minus 5x to the fourth, just using the power rule here. And then y double prime, that's going to be 60x squared minus 20x cubed. And we want to find some critical values and do some sign analysis. So let me set this equal to 0. And to solve this, I can factor out a 20x squared. That's going to leave me with a 3 minus x. And then I see that I have critical values at x equals 0 and positive 3. So putting those both on an f double prime number line or a y double prime number line, so 0 and 3, critical values. Let me test something to the left of 0, like negative 1. Now I'm going to use this factored version of y double prime. And this first term, 20x squared, we know that's guaranteed to be positive since you're squaring whatever goes into there. So really it's just down to this 3 minus x part in terms of figuring out what the sign is going to be. So if we have 3 minus negative 1, that's going to be positive. And then something between 0 and 3, how about positive 1? 3 minus 1 also comes out positive. Something bigger than 3, how about 4? 3 minus 4 is now going to be negative. So we see that f double prime or y double prime is only changing sign at x equals 3. Therefore, y has a point of inflection at x equals 3 only. Looking at our answer choices, we have only a single answer choice with y or with the x value positive 3. That's choice B. You could plug 3 back in to get 162 in the original function, but there's no other options, so we're going with choice B. On this problem, I have a function defined as 3x to the fifth minus 5x to the fourth, and I want the x values of my points of inflection for f. So I'm going to need to figure out where f double prime is changing sign. Let me get f double prime first. So f prime, because we need that before we get f double prime, is going to be 15x to the fourth minus 20x to the third. And now taking one more derivative, f double prime, that's going to be 60x cubed minus 60x squared. And we're just going to set this equal to 0 and find critical values. So this one's pretty easy. I can factor out a 60 and an x squared, leaving me with just x minus 1. So I see that my critical values are going to happen when x equals 0 or positive 1. Putting those both on an f double prime number line now to do some sign analysis. Let's test a number less than 0, like negative 1. And I'll use this factored version of f double prime. And the 60x squared part of this, we know this is always coming out positive. So we don't have to really look at this when we're doing sign analysis. So it's just the x minus 1 that we're looking at now. If I plug negative 1 into that, that comes out negative. And a number between 0 and 1, let's try 1/2. 1/2 minus 1 is going to come out negative. And a number bigger than 1, like 2, 2 minus 1 comes out positive. So I see here that although I have two critical values, f double prime is only changing sign at x equals 1. Therefore, x equals 1 is the x value of a point of inflection for f, which is going to give us choice C. On this one, we're given f, the function whose derivative is f prime equals sine of x cubed, and they give us this nice little interval here. We want to know how many points of inflection this graph has on the interval, or how many points of inflection the graph of f has. So in order to figure this out, since this is a calculator question, I'm just going to figure out how many times f prime reverses direction. Normally we would find points of inflection by seeing how many times f double prime changes sign, but a sign change in f double prime just means a reverse in direction for f single prime. So let's graph this out and see what's going on. So I'm here on my graph. I've entered f prime as my y1, and now I'm going to go to window, and I'm going to go from negative 1.8 to positive 1.8, because that's the only window I care about on this problem. And then we go, let's see here, zoom 0. There we go. Let's see what this looks like. Now, again, we're looking for direction reversals. I don't want to say direction changes, but reversals of direction for this graph. And we see on here that f prime changes increasing to decreasing or decreasing to increasing 1, 2, 3, 4 times. Therefore, f has 4 points of inflection on this interval, which gives us answer choice C. On this problem, I'm given this f of x function with an a, a b, and a k that I don't really know, but I'm told they're constants. I'm also told that f has a local min at x equals -1 and a point of inflection at x equals -2. Based off this, I want to find the values of a and b. So we're going to do this by coming up with a few equations. Since we have a local min at x equals -1, that means if I plug -1 into f prime, whatever that looks like, that should equal 0. That's going to give me one equation. I can get another equation by plugging -2 into the second derivative and setting that equal to 0. Let me start with f prime, though. That's going to be 12x squared plus 2ax, because a is a constant, so we just treat it like that, plus b, and then k is a constant, so that gets zeroed out by differentiating it. And I know that if I plug -1 into this f prime, the whole thing should equal 0. So I can write 12 times -1 squared plus 2a times -1 plus b, all of that equals 0. And if I clean this up a little bit, I can say 12 minus 2a plus b equals 0. But there isn't really much else I can do on this because I still have two variables. All right, so that's where the point of inflection is going to help us out. So here was f prime. Let me find f double prime now. Using the power rule again, that's going to be 24x plus 2a. And I know that if I plug -2 into that, since I have a point of inflection at -2, if I do 24 times -2 plus 2a, that should give me a value back of 0. Well, if this is the case, that means that -48 plus 2a equals 0. So 2a is the same as 48, which is to say that a equals 24. Well, since we know what a is, we can go back to this equation here and plug in 24 for a. So we have 12 minus 2 times 24 plus b equals 0. This is 12 minus 48, which is -36. So therefore, b must have a value of +36.